So what if the ropes don't make the same angle? How do we deal with it then? Let's suppose the traffic light is hanging from two differently angled ropes. For this example, let's assume the traffic light is 10 kilograms and the left side of the rope has an angle theta L of 53 degrees from the vertical, and the right side of the rope has an angle theta R equals 37 degrees from the vertical. I'm stressing from the vertical because that is where our angle is being measured from. So if our angle is being measured from this angle right here, this is our theta, then that's going to make the vertical component adjacent to the angle, touching the angle, and that's going to make our horizontal component opposite of the angle, which means this will be sine and this will be cosine. So it becomes flipped. So you have to be careful how you're reading this. Don't draw the angle from the ground, because if you drew the angle from the ground, that's how you would get your cosine and then sine. But because our angle is being measured from the vertical, we have adjacent and opposite. And we're trying to find both tensions in the rope. So tension is a force, so first step in solving a force problem is going to be starting with a free body diagram. And there we have it. Now we can draw in our components. As promised, the vertical is cosine, and the horizontal is sine. Everything on the left equals everything on the right. Everything up and down equals each other. Not moving, no acceleration, we're in equilibrium. So next up, we're going to plug in the horizontal equation and we're going to solve for one of the equations, or one of the tensions. So this is somewhat new. We haven't done this specifically yet, but it's not any new math that you're having to learn, anything like that. What we mean is we're going to take TL times sine of theta L, which from our problem, theta L was 53 degrees, theta R was 37 degrees. So we're going to plug in those thetas and take the sine. So sine of 53 will give us 4/5. Sine of 37 will give us 3/5. And we get a relative tension on the left. And the tension on the left equals 3/4 of the tension on the right, which is not useful in the least. I mean, just as an answer. So we still have two things here. We're just defining TL in terms of TR, but that doesn't really tell me numerically what exactly TL is. So now we can go to this vertical equation and we can plug in what we just solved for. TL is 0.75 times TR times cosine of 53, which is 3/5, plus all of this mess here, TR times cosine of 37, which is 4/5, equals mass, which was 10, G is 10, equals 100. And then going through and solving to get TR equals 80 newtons. Try this problem again. Make sure you're able to get to that answer. There's a couple, it's not exactly new like I say, but some nuances that if you're not careful, you can easily mess this up. And there's no reason to mess it up other than being sloppy, because it's pretty easy. You know, it's in equilibrium. We're not moving, nothing's changing. So now we can go back and we can solve for 0.75. We just got 80 newtons as our TR, so we can get the actual numerical answer. TL equals 60 newtons. Go back, try this again. Here are some takeaways. The rope with a greater tension is the rope that is more vertical. More vertical, we're going higher, so there's more tension here. You can try this out in class if you want to grab some fishing line and connect to a mass and hang at two different angles, so that way you can kind of feel. We'll do that. Just ask. The lengths of the individual ropes do not affect their tension. Only the angles affect their tension. That's it.